Thank you very much, Mr. Chairman. Good afternoon, everyone. So we have seen in all the presentations today some maps using 3D geospatial data. I will now go to the other side, to the side of the producers of those maps, and try to explain a little bit how and what we get. This is actually the work of the group at the Faculty of Civil and Geodetic Engineering at the University of Ljubljana, a private company, Geocodis, and research center of the Slovenian Academy of Sciences and Arts. So I will speak a little bit about the geoinformational support in disaster response and risk management, basically on flood detection from satellite images, or a fully automatic system for detection of water bodies from satellite images. 3D city and landscape models, so how to generate and use them, and in the end, damage assessment and disaster response planning. So we are, of course, very aware of the value and importance of geospatial data that are crucial in disaster response and risk management. Besides what happened, we want to know where it happened, what was the extent of the events. And the challenges are that we are dealing with three-dimensional data. We are not dealing just with the maps, although we have seen here a lot of very beautiful maps. Behind all those maps were three-dimensional data that we need to generate. Luckily, technological advances have driven the evolution and reduced the costs of getting those data, and I will a little bit speak about those events. At the moment, the Copernicus system, the European Union Copernicus system with the Sentinel satellites, is the most sophisticated Earth observation system ever built. And this is not just my opinion, this is not just the opinion of Earth observation specialists in Europe. These are the messages that we are getting from the US, from NASA, from the JAXA, the Japanese, the Indians, the Chinese, everyone. Just to remember that in a little bit more than 1 month we have European elections, and Copernicus would not be possible without Europe. Not a single nation would be able to build such a complex Earth observation system ever. And we should be proud of this system. So in this system, we have a series of satellites divided into 5 groups, observing everything from land, atmosphere, and sea. We have the Sentinel-1, which is an all-weather radar satellite. We have Sentinel-2, which is a high-resolution optical satellite. High resolution means here 10 meters resolution. We have Sentinel-3, which is intended for atmospherical measurements and higher optical measurements with lower resolution, and then we have 2 satellites mostly dedicated to the atmosphere. At this moment of time, in 4 groups, at least 1 or 2 satellites have been already launched. I will focus mostly, of course, on Sentinel-1, which is a radar satellite, because we are observing water bodies or flood events, and those happen usually when the skies are cloudy, and optical satellites are cannot be used in that case. We need radar that penetrates the clouds and reveals what is hidden from above. So I will speak a little bit about Sentinel-1. We have two satellites in this series, Sentinel-1A and Sentinel-1B. They have invented very stupid names. The next 2 satellites will be Sentinel-1C and D, and so on. But anyway, we have developed a fully automatic system for mapping water bodies from Sentinel-1. We are just mapping or observing the water on the surface. So we are downloading the data from the Sentinel hub immediately as the data is available. That's usually 2 to 3 hours after the acquisition, because we are not the emergency mapping service. They are getting the data 15 minutes after acquisition. We have to wait that they use the data for their own purposes, but this is enough for our purposes. Then we are doing geometric processing with different tools. We are then doing water detection and filtering. I will a little bit speak about this later. And then we are doing spatial modeling and production of time series of those data. Of course, we are disseminating this via web-based web mapping system. So it all starts with a radar image, which is large. It covers almost the whole Slovenia, and we can get those images at least every 5 days. Actually, every 5 days at the equator, but in our latitude, we are getting images 2 or 3 days apart for every point on the ground. So we are then starting for existing water bodies, and radar has a very excellent property for detecting water bodies. They are dark on the images, as you can see here. So basically, we just have to we just have to detect those dark areas. Just is a nice word for using artificial intelligence to start with existing water bodies, then expand those water bodies, and use also digital elevation model and post-processing. At the end, we are producing maps like this. So we are filling the gaps that we're not detecting. We are eliminating smaller patches that can be caused by shadows of trees or that are not important for our cases. But at the end, we are distributing this data via web-based service, which is located at the address whereiswater.at. We also have a Slovenian version, which is called voda.kje.si. And for this mapping service, everyone can get the data for a week. The registered users can get the data for 3 months, and the paying customers are getting the data for the whole period. And here I'm talking the period from 2014 to up to today. So we are not having 100 water levels, but we are having 6 years of water levels. Every at least 5 days, we are generating the products per weekly basis. So here you can see for a point over there near the Cerknica Lake, where we have detected water. The bars that have no water are the times where the satellite did not overpass this area. So you can see here the evolution of water in the area. So we are detecting water bodies from space in real time. But then we use also other data, 3D city and landscape models. And those are generated from different sources. We are using aerial orthophoto, photogrammetric techniques like dense image mapping, either from airborne or from UAVs to generate digital elevation models. We are, of course, using aerial and terrestrial laser scanning data to get the point clouds, and then digital elevation models or building models. So this is actually our faculty here, scanned by a laser scanner. So at the end, we are modeling this data to get 3D city models or 3D landscape models. So we are starting with surface modeling, but then we are improving the quality of the data, and at the end, with different levels of details of buildings. Here we are talking about levels of details, a little bit different terminology as in BIM, to the indoor modeling. Indoor modeling is of course, the next step, and we could use similar techniques to build to extract also the interior of the buildings. I will a little bit speak about the problems later, and have in mind this indoor modeling that is different. So once we have detailed 3D models, we can use flat simulation scenarios like different levels of waters here, or simulation about the dam height. We have heard today a lot about the problems and measures, and here we have a direct measure of how this is important, and how this can influence the extent of water discharge. And of course, we have 3D buildings, and we can observe the areas that are covered with water or flooded, obtained from satellite data, and here simulated with the 3D models. We can not only see which buildings are in the water, we can also see the level of water in those buildings. And this is of course, important for assessment of damage. There are, of course, many challenges here. We have not touched subsurface building modeling yet, or we have just discussed this at the moment. We can have several buildings that are off the water on the ground, but are flooded below, and this is the next big challenge. Of course, we are also integrating all other available data, statistical data, land administration data, land cover data, and so on. We are now talking about the integration of BIM and GIS, or actually the so-called geo-BIM. These are two worlds that are coming together, but as you have already heard, we are speaking different language, and we have to speak a lot together. So to conclude, the fully automatic real-time water bodies detection system is operational for Slovenia. We have the data for the last 6 years. We have demonstrated this in several European and African regions. And we can process this data for any region in the world because sentinels are imaging the whole world, all continents, and we just have to reprocess or process the data for other regions. The inclusion of 3D, either city or landscape models, is relevant for damage assessment, disaster response. Of course, we have heard about firefighters and so on, and also about damage prevention. So my message would be that real-time Earth observation data processing and 3D modeling is actually an essential tool in disaster risk management in built environment. Thank you very much.
Thank you very much.